When installing a 1000 kilowatts generator for whole building backup to a 277/480 volt service, several grounding and bonding considerations are critical. The generator is backing up a large grocery store. The utility provides 12,470 volts to the transformer primary, and the customer owns the transformer. A 1600 amps 3-pole, solid neutral transfer switch is located outside, near the generator and transformer. The building's main distribution panel, or MDP, is inside 75 feet from the transfer switch. Let's address the grounding and bonding questions. Firstly, regarding generator grounding, if the transfer switch is a 3-pole design, the generator frame and neutral should not be grounded at the generator itself. Instead, the main service bonding at the building's main distribution panel establishes the ground for both the utility service and the generator service. This approach prevents the generator from being classified as a separately derived source. A separately derived system requires its own grounding electrode system and bonding, which is unnecessary in this configuration. Secondly, considering the main bonding jumper and neutral bonding, the main bonding jumper should be established at the MDP. With a 3-pole transfer switch, the neutral at the transfer switch and throughout the building remains floating. The main bonding jumper at the MDP provides a solid ground reference for the entire system. The transformer secondary neutral should also be bonded to its frame. Given that the customer owns the transformer and it's not the utility's responsibility, this bonding step is crucial. Bonding the transformer secondary neutral to its frame ensures proper grounding on the utility-fed primary side. Here are some additional points to consider. Firstly, ground fault protection, or GFP, breakers are installed at the transformer secondary, protecting the feed to the transfer switch, and a main breaker with GFP is located in the MDP 100 feet from the transfer switch. A breaker without GFP protects the generator's feed to the transfer switch. The GFP breakers at the transformer secondary and in the MDP must be coordinated effectively. Proper coordination prevents nuisance tripping, which can disrupt power unnecessarily. This coordination involves setting appropriate time delay and pickup current settings for each breaker. Secondly, the generator should have a neutral disconnect or blocking device. This device prevents potential backfeed into the utility system during normal operation. Backfeeds can create hazardous conditions and disrupt the utility grid, so the safety measure is essential. Thirdly, the transfer switch needs regular testing. Routine testing ensures proper operation and seamless transfer between the utility and generator sources. This includes verifying the switch's mechanical operation, control circuitry, and voltage sensing capabilities. Regular maintenance prevents unexpected failures during critical power outages. Now let's delve deeper into the technical aspects of each point. When dealing with generator grounding, the key principle is to avoid creating multiple ground paths. A 3-pole transfer switch isolates the neutral from the generator when the utility power is available. If the generator neutral were grounded separately, it would create a parallel ground path with the utility's neutral to ground connection. This parallel path can lead to circulating currents, causing electromagnetic interference, or EMI, and potentially damaging equipment. By allowing the MDP to be the single point of grounding, we ensure a clean and reliable ground reference for the entire system. For main bonding jumper and neutral bonding, the NEC, or National Electrical Code, provides specific guidelines. NEC Section 250.24 B addresses the grounding of the secondary neutral of a transformer. It mandates that the secondary neutral be bonded to the transformer frame and to the grounding electrode system. This ensures that any fault current on the secondary side has a low impedance path back to the source, facilitating the rapid operation of overcurrent protection devices. The main bonding jumper at the MDP, as described in NEC Section 250.28, connects the equipment grounding conductors to the grounded conductor, which is the neutral. This connection is crucial for creating an effective ground fault current path. The size of the main bonding jumper is determined by NEC Table 250.102. C1, based on the size of the service entrance conductors. Moving on to GFP coordination, Ground fault protection is designed to detect and interrupt low-level ground faults that may not be cleared by conventional overcurrent devices. These low-level faults can persist and cause equipment damage or create a fire hazard. However, if the GFP settings are not properly coordinated, a fault downstream can cause the upstream breaker to trip, shutting down a larger portion of the system than necessary. Coordination studies involve analyzing the time current curves of each GFP device and ensuring that the downstream device trips before the upstream device for any given fault current level. This is often achieved by setting different time delay settings, with the upstream device having a longer delay. The generator's neutral disconnect or blocking device is a critical safety feature. Without it, when the generator is running and the transfer switch is in the generator position, the generator neutral would be connected to the utility neutral through the building wiring. If there were a fault on the utility side, fault current could flow back through the generator neutral, potentially damaging the generator or creating a safety hazard. The neutral disconnect device, typically a contactor or switch, opens the neutral connection when the generator is operating, preventing this backfeed. Regular testing of the transfer switch is essential for ensuring its reliable operation. Transfer switches can fail due to mechanical wear, corrosion, or control circuit malfunctions. Testing should include visual inspection of the switch components, verification of proper operation of the switching mechanism, and testing of the voltage sensing and control circuits. Load testing, where the generator is connected to the building load and run for an extended period, is also recommended to verify the generator's capacity and stability. Let's consider some practical examples. Suppose a ground fault occurs on a branch circuit in the grocery store. If the grounding and bonding are properly installed, the fault current will flow back to the MDP through the equipment grounding conductor. The main bonding jumper at the MDP provides a low impedance path for this current, causing the branch circuit breaker to trip quickly, clearing the fault. If the grounding were inadequate, the fault current could take a longer, higher impedance path, potentially causing voltage rise in the equipment grounding system and creating a shock hazard. Another example is a ground fault on the transformer secondary. With the transformer secondary neutral bonded to its frame, the fault current will flow back to the transformer through the grounding electrode conductor. This low impedance path will cause the GFP breaker at the transformer secondary to trip, isolating the fault and protecting the equipment. Without this bonding, the fault current might not be high enough to trip the breaker, allowing the fault to persist and potentially damage the transformer. Here are some common mistakes to avoid during generator installations. Firstly, failing to properly size the grounding conductors. Grounding conductors must be sized according to NEC Table 250.122, based on the size of the overcurrent protection device. Undersized grounding conductors can overheat and fail during a fault, compromising the safety of the system. Secondly, neglecting to bond the transformer secondary neutral to its frame. This is a common oversight, especially when dealing with customer-owned transformers. Without this bonding, the grounding of the utility-fed primary side is compromised. Thirdly, improper coordination of GFP devices. This can lead to nuisance tripping and unnecessary shutdowns. Coordination studies should be performed by a qualified engineer to ensure proper settings. Fourthly, neglecting to test the transfer switch regularly. Transfer switches are often overlooked during maintenance, but they are critical for reliable emergency power. Regular testing can identify potential problems before they lead to a failure during a power outage. In summary, proper grounding and bonding are essential for safe and reliable operation of a 1000 kilowatts generator in a 277/480 volts backup power system. Following NEC guidelines and best practices, and paying attention to details such as GFP coordination and transfer switch testing will ensure that the emergency power system performs as expected when needed. Remember that electrical work should only be performed by qualified and licensed electricians.